Well, good evening and welcome to our sixth HBY and math webinar. This is a 14-month series with Dr. Sten Odenwald. I'm Dr. Hillary Davis, and I'm the host, I guess. And can you see my screen okay?
Yep.
Okay. And let's see, I should probably make it big. There we go. So I'm a curriculum specialist for the Heliophysics team at Goddard. And Christina may or may not be joining us. I thought I saw her, but I didn't admit her, so maybe she wasn't there. So please introduce yourself if you'd like out loud or and then you can remember put in questions and answers. That's the way it works with the webinar. And we've planned for an hour. And this is the public folder down here. And then I had a quick poll on what level will you use Helio in math? So I'm going to launch that poll because that's helpful too. No, it's not letting me launch. Wonder if I have to stop sharing. Let me try that. Nope, that didn't work. Try something different. Well, why don't you just share what level you want to use it? Introductory, exploratory, or advanced, and that will let Sten know where to focus mostly. There's polls and quizzes. Not working. So you can put it in the Q&A because you're blocked from the chat during a webinar. So Tom, I know you're going to use it with upper elementary, but you'll probably always also share the high school problems with people, right?
Yeah, do you want to go ahead? I guess chat's been disabled, so just verbalize where I'll be using it.
Yeah, the chat doesn't work in the webinar.
Okay, no worries. So what I plan to do is, yes, integrate it into interdisciplinary thematic units of instruction for 5th and 6th grade students, as well as thinking about how I can help as head teacher, as lead teacher, head little singer, work with preschool through 6th grade to make sure that we have, these. I know it's a stretch, but that's what we do, and think about the next generation science standards, and then looking at through the heliophysics lens and how we can integrate it across the different strands of science. The other thing is that I work with sister schools through the NASA EASY mission and the NASA Parker Solar Probe mission, and so this heliophysics big year, of course, ties right in with what we've been looking at with both of those. EASY, I work with Second Mesa Day School up in the Hopi Nation, and then Greasewood Springs Community School, about 60 miles to the east of us here within the Navajo Nation, and then Ku'aklaw Charter School. And all of those teachers work with elementary and upper elementary into middle school. And so I'll be sharing with them this information there. And then with the Parker Solar Probe, it's the Chief Leschi School with the middle school there. And then Whatcom Intergenerational High School, just north of Seattle and Bellingham, Washington. And then there's another charter school north of Honolulu that integrates Hawaiian culture and language. And then Lukachukai here in the Navajo Nation. And so I'll be sharing the heliophysics information with them as well.
So, Judd, did you want to share? And Hiba, I was wondering, but you seem to be someplace where you don't want to talk, which is okay. All right, so now I'm going to go back to sharing my screen. If you have any questions, put them in the Q&A, which is also at the bottom because the chat is disabled in a webinar, not in a regular meeting, but a webinar. So I was showing you this slide, which has the link to it, but the next slide has an introduction to Sten. And so I think some of you know him, but he has a bachelor's degree in astronomy from Berkeley and a master's and PhD degrees from Harvard in infrared astronomy. And he was investigating star forming activities in nuclear regions of the Milky Way. And he has been a space science. He worked at the Space Science Division of the Naval Research Lab. He worked on the NASA's Cosmic Background Explorer mission. He was director of education and public outreach for NASA Image mission. And he just basically follows all the missions, which is great fun because he's always telling the rest of us what the latest developments are. He also developed this awesome website, if you haven't seen it, Space Math at NASA, which has just tons of problems, all organized by math standards and related to the missions. So it's just a brilliant resource. And then he's currently on the NASA HEAT team, where I am also. And he has recent books, The 23rd Cycle, that's the current solar cycle, Patterns in the Void, Why Nothing is Important, Interstellar Travel, An Astronomical Perspective, and Exploring the Heliosphere from the Sun's Core to the Interstellar Void, which is great for our team as a heliophysics team. He's received lots of awards and just is generally widely known for his work, both as a researcher and as an educator. So this is the, I'm hoping you can see this. It's sort of blocked a little bit. Okay. If you wanted to use the QR code, this is the recording from the completed webinars, and I will add this one tonight when we're finished. So I'm going to stop sharing and go back to Sten. And do you want to launch your
Okay.
PowerPoint?
Getting really good at this. Let me see. Oh,
There
got
you
it down
go.
here
Great.
to share presentation. And there we go. Hi.
All
Okay.
right. And I'll keep monitoring the Q&A if you have questions. You're all unmuted, so you could also just interrupt. It's nice to have such a small group.
Well, welcome to the Heliophysics Big Year. It's a 14-month celebration of all things solar. It began with the last year's annular eclipse in October, and it's going to end next December when the Parker Solar Probe reaches its closest point to the sun, about 6 million miles or so, which will be very exciting. What is heliophysics? You actually won't find it in the dictionary, so don't bother. Let me tell you what heliophysics is, because you're likely to hear a lot more of this word in the coming years. Basically, it's a subject that deals with the matter and energy in our sun and how this matter and energy flows out through the solar system and influences planetary atmospheres, magnetospheres, and basically does sometimes some rather crummy things to our technology in space. So it's a subject that ranges far and wide and has some fairly interesting human impacts associated with it. We tend to call those human impacts the aspect of heliophysics called space weather. And you might also have heard that term over the last, I guess the last 20 years since it's been in vogue. As I said, Heliophysics Big Year started with the annular eclipse in October, and it's ending next December. We have decided that it would be fun each month, to identify a particular theme related to the sun that we could talk about. And in my particular area is math education. So I essentially took these themes, scratched my head, and tried to figure out an interesting math component to these fairly diverse topics. Performance art, that one really stumped me for a while, but then I figured out something that I think is going to work really well as a math activity for performance art. We've already done about 6 of these episodes. This is the 7th for April. I wanted to do a lot more about the current solar eclipse that we saw last week, but I began to realize that it wouldn't really work well with the dates that we have for these presentations, which are on like the 16th of each month. So what I did as the next best thing is I came up with a topic that's related to total solar eclipses that I think you might all find interesting. But anyway, NASA sort of organizes its heliophysics outreach in terms of 3 big questions. What causes the sun to vary? How do the Earth and the heliosphere respond to those changes? And what are the impacts on humanity? These are the big questions, and they form the major three big questions for what we call the framework for heliophysics education, which is a way of looking at heliophysics content from the teacher and classroom perspective and see how the various concepts in heliophysics map into the national science standards. This is a way of doing that. Not only do we have the three big questions, which are all designated by the number 1 for some stupid reason. There really are 3. But we also have sub-questions that are more guiding questions, and those are the ones that sort of relate to selections of science standards within the national science standards, layout. The one that we can do tonight, and the one that I'm going to cover tonight, is number 2.3, which is the sun is the primary source of light in our solar system. There aren't really standards that relate directly to eclipses as such, so you have to kind of read between the lines and find things that essentially can be modified to include eclipse science a bit more explicitly than perhaps what the guiding question suggests. Mm-hmm. Well, of course, we were in different places in North America to view this eclipse on April 8th. If you were on the path of totality, you saw something like the large splashy image that you see here. But if you were like me, you were somewhere else. I got to see basically a very thin crescent at 90% coverage, which was very exciting. My friends and I, family, we were out in the patio, looking at the sun with our solar glasses and having a great time. It's amazing how few people have actually seen a partial solar eclipse. So, it's always an interesting thing when even something like that happens. The curious thing about total solar eclipses, and that's what we're going to talk about tonight, is that, even though there are a couple of them somewhere around the world every year, the circumstances for producing one are actually pretty precise and not that easy to come by. First of all, the moon is tilted in its orbit relative to the plane of the Earth's orbit. So that means that there are only 2 places in Earth's orbit and in the orbit of the moon where the sun could actually be present at the same time as the moon is on those 2 spots. These are called the nodes. And the rest of the time, as viewed from Earth and as viewed from the surface of Earth, if you look up in the sky, you'll see that the moon's path relative to the sun's path is tilted at about 5 degrees. So, the circumstance for the moon to be passing across the face of the sun only happens literally twice in one of these situations. So that's basically why you get so few of these. You don't get one total solar eclipse every new moon, which is what you would normally think. And that would be the case if the moon's orbit were not tilted with respect to the Earth's equator and the orbital plane of the Earth. If it were exactly in the plane, we would have a total solar eclipse basically every single new moon. We also have to factor in not only that the moon's orbit, the moon's orbit is elliptical and intersects at 2 places, but we also have the fact that the Earth orbits the sun in an elliptical orbit, which means that its distance from the sun changes, and that means that the size of the sun as viewed from the Earth also changes. During aphelion, when the Earth is farthest from the sun, the apparent size of the sun appears to be the smallest, and during perihelion, when the Earth is closest to the sun, it appears at its largest angular size. And so we have these 2 circumstances going on with the size of the sun as viewed from the Earth. And also we have the fact that the moon's orbit is elliptical as well. So it has a perigee where it's closest to the Earth, and it has an apogee when it's farthest away. So the circumstance when the sun and the moon are just exactly the same angular size depends on whether or not the Earth is at aphelion or perihelion, and whether or not the moon is at perigee or apogee. So that's where things get a little bit complicated. And that's why we have, quite a few annular eclipses where the moon is smaller than the apparent size of the sun, and we have a few that are total, where those sizes just happen to be exactly the same as viewed from the surface of the Earth. Here I show a comparison of the moon size at perigee, at closest to the Earth, and at apogee. Sometimes the media likes to call the perigee moon a supermoon, and I guess the apogee moon would be a mini moon or something like that. I hear supermoon being used quite a lot. And they say, oh, if you go outside and look at the full moon, it's the biggest that it's ever been in 3 years. And it's like, okay, people are expecting to see like what, the moon filling up the entire sky, I guess. But no, the difference is only about maybe 5 or 10% in apparent size, which if you're not somebody that looks at the moon a lot, you might not even notice that it's a perigee moon or an apogee moon at all. And it just looks like a full moon as far as you're concerned. Also, the perihelion and aphelion apparent size of the sun changes appreciably, as you can see in these two photos. At perihelion, as I said, the Earth is in its orbit about 5% closer to the sun, and at aphelion, it's about 5% farther away. So that difference translates into an apparent size of the sun that changes. So you have, as I say, the size of the sun apparently changes, and the size of the moon apparently changes as well, as viewed from the surface of Earth. Also, this issue of the orbit of the moon, as I said before, is very important because as viewed from space, if you were to look at where the shadows of Earth and moon fall, first of all, the shadows don't look like cones. I mean, you'll probably see a lot of drawings that seem to suggest that the sun is like a giant lens that's focusing a beam on the moon, which then focuses a pinpoint shadow on the surface of the Earth. In fact, by the time the sunlight gets to the orbit of the Earth, the rays of the sunlight are almost parallel. So that means essentially the shadows of the Earth and moon are almost parallel cylinders in space. And when those cylinders intersect, then you get shadows on essentially the surface of the Earth. If the moon happens to be between the sun, and the Earth, or you'll get a much bigger shadow if the Earth happens to be between the moon and the sun. You'll notice that the Earth has a shadow that's about 2, 3, 4 times bigger than that of the moon, and that means that if you were to look at the moon during a lunar eclipse, that eclipse would be apparent over a much larger part of the hemisphere of the Earth than the path of a total solar eclipse, which is a very narrow band. So you can see a lot of total solar eclipses every year, 3 or 4. But total solar eclipses are much more rare because of the narrowness of the moon's shadow projected onto the surface of the Earth. Now, we have an interesting problem. The moon is not stationary in space, but is actually drifting away from the Earth. So over time, the moon is getting farther away, which means that as viewed from the surface of the Earth, the apparent size of the moon is steadily getting smaller and smaller. But that's over the course of tens of millions of years. Okay? But still, if you're a stickler for details and you want to calculate total solar eclipses, you have to factor in the fact that the moon's orbit is expanding, getting larger. And so the angular size of the moon is consistently getting smaller and smaller as the millennia go by. So that raises kind of an interesting question. When did we have our first opportunity in geologic history to have a total solar eclipse? And when are we likely to no longer have total solar eclipses because the moon is too far away and or the sun has changed its size so that you no longer have the exact angular size relationship that you need? So once we get to that point, there will no longer be total solar eclipses because, like they say, you can never go home. You can never go back. You know, once the orbit expands outwards, it doesn't somehow miraculously contract back in. That kind of physics does not exist in our universe. So what we're going to do in the next couple of examples here is we're going to do some little calculations. First, I want to start with the whole concept of angular size, and this is a really basic thing. You know, angular size is sort of an important concept in astronomy because we use that to gauge the apparent separation between things that we see in the sky. But we also use it sort of on the terrestrial scale because anybody that has basically taken their thumb and put it out at arm's length to cover up a skyscraper on the horizon, you know, knows that angles in similar triangles can be the same, even though the distances and the sizes of the objects vary enormously. You have no doubt heard that the circumstance of our moon's apparent size being similar to that of the sun, that is their angular sizes, is a consequence of the fact that even though the moon is about 400 times smaller in physical diameter than the sun, it's also 400 times closer. So the proportion is unity, which means that the angular sizes of the sun and the moon are comparable to each other. But of course, as they say, the devil is in the details. And in order to get a total solar eclipse, they don't have to be just approximately the same in angular size. They have to be exactly the same in angular size. Otherwise, a little bit of the sun's bright photosphere will peek over the limb of the moon, and you'll no longer have a total solar eclipse. So anyway, that's this example is, you know, showing diagrammatically this idea of arm's length fingernail is about the same as the moon's apparent angular size in the sky, given that the moon is 380,000 kilometers away. Similar triangles explain it all and account for the fact that the angle is the same, even though the distances and sizes are vastly different. And you can do this calculation yourself. It's a good beginner's calculation. It can be done diagrammatically by drawing a scale model on a piece of paper and working from that. Arm's length 24 inches, your fingernail is 1/4 of an inch, and so you do the proportion, and the angle is about 0.6 degrees. But the moon is its diameter and its distance, which also turns out to be 0.6 degrees. So your thumb very neatly covers, or 1/4 inch, that's kind of like your pinky, your little finger. If you put your little finger out at arm's length, it would cover the full diameter of the full moon. Intermediate level problem, we could actually do this calculation more exactly using a very often used formula in astronomy. I consider this one of the fundamental equations in astronomy because we use it in so many different guises. Basically, when we convert from physical size to angular size or vice versa, most of the things that we're describing have very, very small angles of less than a degree, which means that if you form the triangle and the angle opposite the distant side, if you make that angle small enough, you can get away with using what's called the skinny triangle relationship. And that means that the angle is basically just 57.3 degrees, which is 1 radian, times the ratio of the linear diameter of the thing divided by its distance. This formula for things that are less than a few degrees in angular size works with a precision of better than 5%, plus or minus 5%. So that's why we use it as sort of a first guess at how far apart things are or how big they are, given that we know that the distance to the object and we also know what their angular size happens to be. So here are a couple of examples. For the moon with a diameter of 3,500 kilometers and a distance of 363,000 kilometers, you plug in those two numbers into the relationship for theta and you get 0.55 degrees. If you prefer to use, as we do in astronomy, arc second measure, there are 60 arc minutes to a degree, and there are 60 arc seconds to an arc minute. So 1 degree is 3,600 arc seconds. So if we multiply 0.55 by 3,600, we get 1988 arc seconds as the diameter of the moon. We use arc seconds preferably when we're talking about eclipses because degrees are just too cumbersome and too gauche as a unit. Arc seconds are much finer in detail, and we can treat small changes in distance and size very much more accurately using arc seconds rather than degrees. Plus, when it comes to the angular diameter of the sun and the moon, we get things like 1988 and 1856, which are almost like calendar years. So it's kind of funky that way. Anyway, arc seconds for eclipses is sort of the preferable unit. Now, how do we handle the distance to the moon? Well, that comes about from a variety of sources that have looked at this issue very carefully. They measure the current distance to the moon over a period of years, work out that the moon is receding at about 3 centimeters per year. They go back even farther in time and discover that the Earth basically has been rotating faster as you go back billions of years. The typical day used to be about 18 hours long about 4 billion years ago. Now it's about closer to 24 hours long. And over that intermediate period, there's geologic evidence that lets you figure out, sort of in a somewhat indirect way, what the apparent distance to the moon is over this time. So over the last 1 billion years, the distance has changed from about 300,000 kilometers to the current value of 363,000. So what we want to do is we want to make a linear model for that mathematically. And so that basically turns into something like this. We have to calculate the slope, which is the final distance minus the initial distance divided by 1,000 million years, which is a billion years. And so we get about 63 kilometers per million years as the rate at which the orbit of the moon has increased over time. And so then we can create the linear equation. Distance to the moon is 300,000, which is the initial distance, plus 63 times t, where t is the time in millions of years. And so this basically is a nice linear equation that models the way in which the moon's orbit has increased. And of course, now that we've modeled the increase of the moon's orbit, we can put that into our angular size relationship and therefore model what the angular size of the moon is and how it's changed over this period of time. Now, if the sun's diameter is 0.5 degree today, and how many million years will the moon's diameter start to be less than the sun's diameter? Well, that's a matter of setting things up. The sun's diameter is 0.5 degrees today. I'm not even sure what's going on here. Right, and so what we want to do is we want to model how long it's going to be for the moon's diameter to be less than 0.5 degrees, okay? And if you work through this thing, you find out that that time is 600 million years. So 600 million years from now, the moon is going to be far enough away from the Earth that its diameter will be less than that of the sun today, which is about 0.5 degrees. So that gives us our first indication that total solar eclipses, are not things that are going to persist for a long period of time. I mean, you can argue whether 600 million years is a long period of time or a short one. For geologists, it's sort of medium long. 600 million years ago, we had the Cambrian explosion. That's when we went from single-celled organisms to multi-cell. And in another 600 million years from now, arguably, the Earth will be hot enough that most multicellular organisms will not be able to survive on the surface of the Earth. So we're kind of halfway in between these two interesting epochs for life on the planet Earth, which just happen to be mirrored by a period of time when you can actually see total solar eclipses. Now, there's another thing that we need to factor in here that typically we haven't. The previous slide, gets this 600 million year number, and you've probably heard that number before, by astronomers who have been asked, well, how long are we going to have total solar eclipses? And they'll basically say, oh, another 600 million years, and then that's the end of it. In fact, in 2017, I was one of the authors of that number. And it got a fair amount of press back then, and it's gotten a fair amount of press now as well. The only problem is that we haven't really kept up with making this a more precise number. There's one thing that we have forgotten to include in here. I mean, you notice in the first line, it says if the sun's diameter is 0.5 degrees today. Well, the problem is that the sun's diameter is essentially a moving target. First of all, it changes depending on whether or not we're at perihelion or aphelion, and it changes by about 5 to 10%. So it's not a fixed number. And the other thing that's kind of funky about the sun is that the sun is an evolving star. And that means that its size physically is changing over time. It's getting bigger as a star. It's getting more luminous through stellar evolution. And so we haven't included both of those effects in this estimate for 600 million years. So as an advanced problem, we're going to do that. First, we're going to include the fact that the sun's radius is changing, and we can model that with this particular equation. I mean, you can see that the diagram here shows a black line, which is basically a representation of a model for the diameter of the sun. And it shows that it's sort of linear, which is very convenient for us. We're also going to include, as we did before, the lunar distance, but now we're going to finesse it by including both the perigee distance and the apogee distance as models. As I said before, whether you have an eclipse or not depends on whether or not, whether or not the moon is at perigee, at its largest apparent size, or at apogee. And so we're going to include both of those in addition to the fact that the orbit is increasing in size. And that gives us these two lunar relations. The sun's diameter is changing. About a billion years ago, it was 95% of its current size. And a billion years from now, it's going to be 5% bigger. So if we work out a model for the change in the radius of the sun, we get the equation at the bottom, which is R equals 696,000 plus 35t kilometers. Okay, so that gives us a model for the evolution of the sun's radius, which matches that black line on that graph that I showed you. And now what we do is we look at our formulas that we have for the angular size of the sun and the moon. For the sun, the angular size is its radius divided by 150 million kilometers, and we get that equation for theta of the sun. The moon apogee distance changes as we calculated, and we get an angular size for the moon, which is theta A. And we also get a perigee size for the moon, which is theta P. So we have these three relationships for the angular sizes of the sun and the moon as a function of t, where t is in units of millions of years. And so now we can graph these, and we get 3 lines on a graph. And what we notice at point A is point A is about 400 million years ago, and point B is 460 million years from now. Unfortunately, I did not draw these as carefully as I should. 0 is between the minus 100 and plus 100 million years, so I didn't draw the 0 in. But that first dot that you see there is A, and it's at 40 million years ago. That's the condition for when essentially the lunar disk was large enough to just cover the size of the sun at that time when the sun had the size indicated by the red line at that point. And correspondingly, point B is later in the future when the sun has expanded a bit more. And that blue line shows essentially the perigee diameter of the moon. And so that's when the moon is its largest and therefore is able to cover the sun, at least in principle, even though the sun is larger at that time. And if you want to do a more accurate calculation still, what you could do is, first of all, this has been programmed into a platform called Desmos, developed by Luke Henke and myself, and I gave the link for it down at the bottom. But basically, if you replace the lunar changes with a even better equation that fits it more accurately, fits the change in distance more accurately, you get the red region that you see there in the graph. And if you also use the aphelion and perihelion distance for the sun, as the sun changes in its physical size, you get those diagonal lines going up the diagram. And so you have those 2 points, those 2 intersecting points. Point A occurs 437 million years ago, and point B is 252 million years from now. These represent the last time that you could have a total solar eclipse at aphelion, and the last time you will have it at perihelion. And after that, you basically no longer have any total solar eclipses whatsoever, because the size of the sun, which is the sloping lines, is now bigger than even the biggest size possible for the moon, as the moon is getting farther away. So it's a kind of an interesting problem. You can solve it graphically like I did here, or analytically using the equations and putting them in equal to each other and finding their intersection times algebraically. So that basically is it. I'm looking forward to questions that you might have. So let me stop sharing and get back to the main program.
I'm not. You are all unmuted. Thank you very much, Sten. Does anybody have any questions? If you have questions, you can either put them in the Q&A or you can ask them verbally.
Yeah, you might wonder what the Earth is going to be like 250 million years from now. Well, that could be an interesting question for your students. I mean, given that the continental drift cycle is about 250 million years, we won't even have the same continents that we do now. There'll be a new continent that forms, over time. So it'll be a very different Earth, probably even climatologically. So anyway, try not to think too deeply about it.
So Stan, if people don't have questions, do you want to demonstrate? Oh, Tom has a question, or you could demonstrate Desmos a little bit, because it's very.
Well, I just wanted to say that, yeah, that last graph that you had was very helpful for me to understand the dynamics and the additional variables. So
Yeah.
Thank you for putting all that together. That's very
Yeah, if you look at the supercomputer modeling that's been done on the lunar orbit, over the past billion years and progressions into the future, you find that it's not exactly linear at the scales that we're interested in time-wise. So you got to put them in as more, parabolic. That's why they're curved, not straight lines, and that changes the intersection points on the solar diameter plot. But the solar diameter is a factor that people don't realize is an issue when you're trying to calculate the last total solar eclipse, because it's such a gradual thing, nobody really thinks about it too hard, but it's an important factor. As I said, my original calculation using linear things was like 600 million years from now, but now it's as short as 250 million years from now. It's getting kind of uncomfortable. Well, for an astronomer, I mean.
well, yeah, but yeah. No, I hear you. It's but yeah,
it's about
accuracy.
It's about the same time that it'll take the Milky Way galaxy to rotate once.
Okay.
Now,
Now,
I
you
don't know
mentioned
if you want to
earlier,
attribute something cosmic to that, but
you mentioned earlier about the luminosity getting brighter. Can you explain that in the life of a star? Because I wasn't
yeah.
that was not on my radar.
Yeah, the sun is basically going to increase slightly in temperature, but the fact that it's increasing by 5% in radius means that it's increasing in surface area. And because the luminosity, that is the number of watts coming at us from the sun, is basically the surface area of the sun, and it's proportional to the fourth power of the temperature. That means that in 250 to 300 million years from now, the amount of insulation that the Earth gets is going to be 3 or 4% higher than it is now, and that's irreducible. That's heating everywhere on the planet by that amount, which is sort of catastrophic. If it goes up another 10% above that, ocean water is going to tend to want to evaporate into a vapor phase, go into the atmosphere, and become an even more effective greenhouse heating mechanism. So, 250 to 300 million years from now, we're sort of at the beginning of a dramatic change in the heating of the planet Earth, which basically most organisms will have trouble surviving that are used to a more moderate climate.
Wow.
I don't lose sleep over that either, quite frankly. I mean, what can you do?
Well, you're putting it on everyone's radar, so hey, it gives people time to prepare.
Yeah. Well, I prepare. I mean, I'm not even sure. I'm still trying to prepare for my 72nd birthday next November. I mean, I'm not even on the scope for worrying about a million years from now, even though
right.
Anyway. There's an interesting psychological or economic principle called the discounting problem. When people look at when they look at people's brains as they respond to friends, as patients respond to friends, they get certain areas of the brain light up. And when they ask them questions and try to have them think about their future self, they get basically the same reaction. So the argument is that we don't have a special bond with our future self. We view our future self kind of the same way we view our friend, right? And so that's why we have such trouble in paying things forward to ourselves. We want the $100 now instead of the $1,000 in 5 years. And I worry that we have the same problem with these cosmological things. We're not going to worry about ourselves 250 million years in the future, nor should we. Nor should we necessarily worry about our civilization 250 million years in the future. But we should have some kind of feelings about the future.
Sten Hibbert had a question. Can you please re-explain why the lunar and solar sizes vary?
Well, it's if you take your arm, if you take your thumb and put it at arm's length, but then you change slightly your arm's length, you'll notice that your apparent size of your thumb gets bigger or smaller depending on how far away it is from your eyeballs. All right, that's the angular size distance effect. Now, if at the same time your thumb is swelling in size and shrinking in size, you've got these two effects going on. You've got the change in the distance to your thumb, and then you have the change in the size of the thumb. And both of them contribute to the apparent size of the thumb that you see with your eyeballs looking at it. All right.
Am I demonstrating that?
You're demonstrating that, and from where I'm sitting, that your thumb covers your entire face.
Yeah, me too.
Yeah.
Not even getting bigger.
All right.
Okay, and then Abbas had a question. Does the change in the orbit and orientation of the moon and Earth, or the Earth's precession, impact the calculations?
The Earth's precession around its axis does not change anything. It's only the distance to the moon and the distance to the sun. And because both the moon and the sun, well, the moon is in an elliptical orbit with changing distances to the Earth, and the Earth is in an elliptical orbit around the sun with changing distances to the sun. So those are the only two distances that really matter in this. The moon doesn't change its diameter at all, so that's fixed, and that's an easy thing to model, just a constant. But the sun, as I said, changes its physical diameter over millions of years, so you have to actually put that in your calculation.
Okay, good questions. Are there other questions?
Anybody want to talk about black holes? I'm sorry.
I was thinking that you said that a day was 18
Yeah.
hours and now it's okay, so in 252 million years from now, how long will a day be?
Yeah, good question. I worked that out. It's like I don't know, 5 to 10 minutes shorter or something.
No
I don't know.
way.
You know, we're talking, it's a little bit, but we're not talking hours.
Wow.
Yeah,
That surprises me.
yeah. Yeah, you know, if you're going to time travel into the future, you got to reset your watch.
Or you'll miss it. That's my plot line for sure.
You know, so, you know, put that in your things to do list for time traveling.
Okay. Any other questions?
Which is an interesting question. You know, if you're going to time travel and meet somebody at a specific time in the future, you've got to factor in the length of the day in that future date, right? So it's, you know, interesting science fiction story you could write about people missing an appointed date in the future because they didn't reset their clocks properly. You see, astronomers worry about that kind of stuff.
Michael, you joined a little bit late, but I'll send out after this the recording so you can hear the whole thing if you want to.
Okay, well, thank you all for joining us on this post-eclipse evening. And we'll hopefully see you next month.
Thank you so much.
Thanks
You're
for
welcome.
coming.
Y'all have an
Bye.
awesome evening. Take care.
Bye-bye.
Thank you.
Bye-bye.
Thank you.